Andrew, do you want to pick up her boot?
I've got class.
You want to pick up her boot so she doesn't forget it. That way you have less.
Okay. So, we are going to be going over more of the final exam review today. First off, I had some trouble with annotation yesterday. So, share screen. Let's see. Yeah. Why can I not draw on my screen today? Yesterday. What happened to that? Stop share. Okay. Advanced sharing options. Share screen. Settings. Share screen. Advance. Weird. Just have to do as best we can. Okay. So, let's see. Need for polls, none of that stuff. Okay. All right, so is everybody ready to get started with doing the practice exam? We're continuing on. All right. Okay. Chat. Where did my chat go? Alt-H. Seriously, this is getting kind of frustrating not seeing. They updated it and I hate it, of course, is the standard response. There it is. Okay, there we go. Now I've got my chat window. Now I've got this. All right, so first thing we're going to do is that we are going to continue on with this stuff. Okay. I'm just going to use this for Java, for basically Java syntax highlighting. All right. So, complete all of the following prompts. Part of the exam deals with binary trees, constructive nodes of the following class. We've got a key, a data, left and right. That's just some of the way that people do binary search trees, where you have a key where you basically build a map using them. It's not really too important. What we care about is the key, not really the data. All right. A, the Java following method uses recursion to search for a key in a binary search tree whose root node is referred to the parameter root. If it finds the key, it returns a reference to the corresponding data item. If it doesn't find it, it returns null. Here it is in all its glory. Right? This is the recursive method we pretty much have known how to deal with. In the space below, rewrite it so it uses iteration rather than recursion, which is kind of the opposite of what we've been doing, but hey, it's good practice anyway. So, just to kind of deal with it. It's not too bad. So, oh, come on. Here we go. So we've got ourselves our, let's just grab this header, public static object, and now we want to rewrite this so that it does recursion, that it doesn't use recursion. All right, so I'll just go ahead and rewrite this the way we typically do our stuff. Node E public stack E, search E, And we're going to do, and we won't need a key. We'll just simply search for, it's already going to be in there. So so what we're going to do is say, hey, while root not equal to null, this is going to be a bit more interesting, but basically we got to use the same assumption, which is that we assume the thing we're currently looking at is, we make all our decisions locally, and we assume the thing that we're currently looking at is perfectly acceptable. And if we get out of this while loop, we're going to return null because nothing existed. So what we're going to do is say, hey, while root is equal to null, and then we actually just do the standard thing. We just do the standard over here. Oh yeah, we do need a key. So, but we're going to do yeah, why not? We'll do the int key thing here. And we'll do we'll follow their silly directions. If root dot key equals key, then great, we found the node in question, so return root dot data. Else if key is less than root dot key, we don't return. Instead, we say root is equal to root dot left. So we go down the left side. Otherwise, we go down the right side. And that's really all we need to turn it to make it non-recursive, but can get a bit confusing and harder to unwind when you're doing it. Yeah, how do I not need a key? I needed a key. And yes, I'm recording.
Good job.
Okay. Thank you for answering the questions in chat, people. All right. Oh, this one's a much better method because it's much more recursive and much more the type of questions I'd love to ask on the final exam. Write a method called mirror that takes a reference to the root node of a binary tree and creates a new tree with its own nodes that is a mirror image of the original tree. For example, if root is a reference to the root of the tree on the left, then on the right, we're going to return then we're going to return the node on the right. So the tree on the right. So notice what's happened here. Not only has 3 and 2 swapped, but basically so we've also their children have, swapped as well. So basically, and then their children have also swapped. So 4 and 5 went to being on the left side of the tree to the right side of the tree, and 4 and 5 also switched to 5 and 4. So let's think about, so really what's going on here is that basically what I do is that I handle myself. I create a clone of myself, right? And then what I do is I attach my left to my right and my right to my left, and then ask them to mirror themselves. So it's actually fairly straightforward, believe it or not. Let's go ahead and do. In case this is driving it crazy. Which it could be. Yeah, it was. That was what was driving it crazy. So, any questions on understanding this problem? I really like this problem. It's fairly straightforward. Which is that, once you think about it, that we just swap these and mirror them. And the key is that we're creating a new thing. So, let's go ahead and grab this guy over here. Okay. Now, so what we're going to do is that we are going to so if root equals null, and I need parentheses, been working too much in Python for my other class. If root is equal to null, return null. That's just fairly standard, right? If nothing's there, then I'm not going to clone anything. Okay. Otherwise, I'm going to say node new root is equal to new node root.data, because, right, we're creating a new tree with new and with its own, and it says with its own nodes. Okay? And then in the end, I'm going to return that new root, right? Because that's going to be the mirror image. So far, so good to everybody? So what we've done is that if I don't exist, I return nothing. If I do exist, I create myself, I create a clone of myself, and I will return that. So now we need to just handle our children. Well, remember, we're going to handle this all locally. And what happens? Well, my right child becomes my left child, right? Forget about all his nonsense and what goes on over here, but on the other side. But my right child becomes my left child, and my left child becomes my right child. So node new left is equal to new node. Let's see. Oh, yes. We wouldn't create a new node because we already are, because mirror will already take care of that. Mirror, right? Because remember, what if I tried to do this? Root.left.data. Or, sorry, swap it like that. No, I'm not overriding the tree. I am just simply creating a new. I'm just simply I'm copying the data. That's all I'm doing. I'm just copying the data out. Now you might think to do this. But remember, if right is null, then this will give us a null pointer exception. So what we do is that, remember, we make all the complicated stuff the problem of the recursive method. So root.right. So our new left is equal to root.right. Node new right is equal to mirror root.left, right? So our left side is the mirror of the right, and our right side is the mirror of the left. And now we just simply say new root dot left is equal to new left. New root dot right is equal to new right. Can you do this in place? Probably, but yes, you can do this in place, but it's a pain. Yeah, I understand what you mean by not like creating a new tree. You could do it in place, and that just means you just literally swap. And that's just actually just a bit more, and that's just a bunch of swap operations. Basically, right? First you would swap your children's data. And then you would, so first you would swap your children, and then you would have your children swap their own stuff. That's basically it. Right? To do it in place, if you were doing it in place, you'd basically just have your children swap their data. But this is a lot less messy. All right. What is the running time of your implementation of the mirror method? Use big O notation and explain your answer briefly. Well, I'm hitting every single node in the tree. It's O of n time. Basically, what I do is that I check every single node of the tree, and then I ask every node to swap its children, which asks every node to swap its children, which hits every node in the tree, which is a grand total of n nodes. So it's O of n time. Each node gets touched basically only once. Each node gets touched by this function only once, and each call has a composite number, has a set number of steps to do. All right. So for right now, I'm going to go ahead and now go to another practice exam, one that's not listed on there, but one that I really like. Or a series that I really like. Let's see. Is this the one I like? Yeah, why not? Sounds good to me. All right. So Tokyo University is one of the most prestigious, or possibly the most prestigious university in Japan. And Japanese schools are really all about their entrance exams. They love their entrance exams. So this is an entrance exam, as you can read here, for the Graduate School of Information Science and Technology, right? Which was administered in 2016. We can see from the URL here, winter. And it was basically you have 2.5 hours to complete this. It has 4 problems right in it. So let's take a look at these 4 problems in here. Right here, it's just simply, right, that's Japanese, and it says, and you can probably guess what those instructions mean, what they say they are. Blank page, useful for members, do not detach. So, problem 1. A unit lower triangular matrix is the lower triangular matrix whose diagonal elements are all equal to 1. So, answer the following questions. Prove the product. LL is also lower triangular, right? So, for basically problem 1 is just a bunch of math problems about matrices, which is something that you will probably end up doing if you're in a computer science, right? At least if you're going into graduate school. Let's look at problem 2, which looks insane, but it's really not. Let us consider a non-deterministic finite automata with epsilon transitions, epsilon NFAs. That's just simply meaning that basically that transitioning from one state to another can happen without a stimuli with an event. It can have a silent transition for this. So NFAs, non-deterministic finite automata with are just simply more complicated deterministic finite automata, and any non-deterministic finite automata could be turned into deterministic finite automata. And furthermore, all deterministic finite automata are equivalent to regular expressions. So this is just simply, long story short, this is just simply the mathematical form of regular expressions. And this is useful for proving things about regular expressions. So basically it's saying here, it's a regex where the strings are only matching sequences of A's and B's, right? And here is and basically we're saying that we can have any number of A's, 0, 1 A's, followed by 0, 1 B's, followed by any number of A's. Right? So the regular expression for this would be A star, B star, A star. Right? If you know your regex. But hey, now where would you learn this? In automata theory, which is a 4,000 level course. But hey, so there's no expectation for you to know that. But this is actually just, it's a flowchart. It's just a complicated mathematical flowchart that mathematicians created to make it look like what they're doing is really, really hard. Now, granted, proofs are annoying, but we have stuff like called the pumping lemma to handle that. Ooh, problem 3. Answer the following question concerning binary search trees. Okay, that seems familiar. Here, the height of a node is defined as the maximum graph distance from the node from one of its descendant leaf nodes. For example, a node with no children is height 0. So they define height differently when we do. That's okay. There's different arguments of whether like a node with a tree with a single node is height 1 or height 0. So, the height of a tree is defined by the height of its root. So, here what it's saying is that this node is height 3. Really what it matters is are they determining height by the number of nodes, 1, 2, 3, 4, like we've been doing, or the number of edges, 1, 2, 3? And they say we want to determine our height with the number of edges. Make sense to everybody there? So they're just simply asking about binary trees, and they're saying that basically we're counting the height by edges. That's just like a cultural thing, not necessarily to Japanese, but to the mathematicians who created this problem. Okay, suppose we have the following operations in the above tree shown in the shown order: inserting 3, inserting 8, deleting 4, and deleting 9. So if we were to insert 3, that would go boom, that would go all the way over here, and then 3 would go right over here. Why can I not annotate? Zoom annotation. Under meetings, prerequisite annotations enable. So, yeah, so did I turn it off somehow? Let me see. Give me 1 sec. Settings. Okay. Apparently got turned off. So let's see. Stop share. Share. I'd have to stop the meeting. All right. Is everybody okay with me stopping the meeting and coming back and just jumping in literally a minute later so that I can possibly get my annotations back? Because that's what I'm about to do. Okay? All right, stop share. I'm going to stop the meeting now. I'm going to immediately rejoin it. Okay, sorry about that. Let's wait for people to rejoin. I'm going to share my screen, though, and let's see if we've done... Aha, it's back. Great. So I think they must have just updated things, or I changed something, but whatever it was, I fixed it, so that's great. Okay, so how many participants do we have currently? 13, 14. Let's wait for people to join back in. Regardless, I'm recording. But here I can say, here... Now we can add 3. And now, not too hard. Right, I'll go ahead and just add 8 over here because that's not hard at all. Right, 8 is less than 9, but greater than these suckers. So now we've got to delete 4. Doesn't tell us how they want to do the delete operations. So I'm just going to go for the next in order... Because it's going to be the least messy, what I'm going to do is that I'm going to replace the deletion with the next in order predecessor. Because the next in order predecessor of 4 is 3. So all we would do is take the 3 we just added and move it to where 4 is. Okay, 3. And the same for 9. Right? The next in order predecessor is go once to the left, all the way to the right. Oh, look, it's the 8 we just added. So now we've got an 8. All right. So and it wanted us to depict the tree, save the tree after each operation, but we could have just simply done that as we went. Answer the minimum and maximum heights of a binary search tree with n nodes. So with n nodes, so let's just think about it in the way we've been doing, so we don't have to transport it. So where it's the number of nodes on a route to the bottom. The maximum height is n, because it would be one node followed by another node followed by another node followed by another node followed by another node. Right? If we're going by the way that they're doing it, which is edge height, it would be n minus 1, because you would have n nodes, but n minus 1 edges. Okay, now for the minimum height of n, that would be a complete or perfect tree, because those are the most space efficient. And if that's the case, whoops. If that's the case, then that would, if we have n nodes, then we're looking at, then the height is log base 2 of n. Right? So here we have 7 nodes. And then it would be, since it would be a math exam, we'd say the ceiling of it. So here, yeah, it would be the ceiling of that. And if we were going to get the edge height, we'd say -1 again, because we'd be off by 1. All right. So this is a graduate exam, but the questions are very, very familiar, right? Right. This is a data structures exam, or this is a data structures question. It's fairly straightforward. Actually, we call binary search tree balanced if every node satisfies the following conditions. In the case the node has 2 children, the heights of the left and right differ by at most 1, right? So we did this during the exam too. If it has only 1 child, the height of a subtree, in the case that you have only 1 child, the height of the child subtree is 0. Which, remember, that means you can have 1 child, right? Because they're going by edge. Answer the minimum and maximum tree heights for a balanced binary search tree with 7 nodes. Depict a tree with the minimum height and the maximum height. I love these. So, depict a tree with the minimum height and the maximum height for a tree with a balanced binary search tree. So, minimum height would be, if it's balanced, would be like this. 7 nodes, right? That's our minimum height tree right over here. Right? Perfectly balanced. Okay. So now let's see. Now, we only have 7 nodes to play with, so we want to make this as big as possible. Okay. So here, the height of the so if I add another node here, I have to add another node here. Just have to. Because otherwise, if I didn't have that node, this is now unbalanced because we have a height of 0 over here and a height of 2 over here. Whereas as they would say, we'd have a height of 1. Yeah. We'd have this subtree would have a height of 1, as they would say, and this one has a height of, this would be 2 nodes, this would be 0. So that would be not so great. So we have to do this. Okay. And that's that's an example of our maximum height. So minimum height 3, maximum height 4, or if we're going to go with what they're saying, 2 and 3, because we would just subtract 1 for the edge. Okay. Okay. Answer the minimum height of a balanced binary search tree with n nodes. It's the same as the minimum height that we set up, period. It's got to be balanced in order to have the minimum height. Show the height of a balanced binary search tree with n nodes is no more than 2 n log n. Right? So it's just a matter of trying to 2 n. So let's go ahead. So right. We can only make these differ by so much. Right? If we add another node over here, then that means we have to add more nodes over here. So that's kind of the approach that we're going to go through. This is definitely outside the context of the class over here. But again, drawings are pretty good, but they're looking for a more mathematical answer. But look, this is a graduate exam. For the most part, we could answer most of these pretty straightforwardly. Question 4 was on gates. Let's take a look at what else they might have to offer on different years or something like that. So let's go S for lack of a summer. It's a longer exam, specialized subject. Looks like that's a more formal one. Here we have vectors, another discrete automata question, genetic information, which is probability. System. So is this computer science over here? Vectors. Yeah, so those are more look. So from what I've checked out, I only realized just today that I could go and hit S for summer. So, but what I've realized is that basically what I've checked is that like every exam that they've done over the years for winter has had one of these data structure questions. So here, consider the implementation of a priority queue using a binary heap data structure. Note that a binary heap satisfies the following properties. It's a complete binary tree, and each node has at most 2 child nodes, and the number stored in the parent is equal or small, right? It's a min heap, right? So suppose we have the following binary heap, right? Draw what happens, it's saying. So to this heap, as we insert 21 and then 20, as we insert 21 and then 23 and then 26. So here, I don't want lines, I want wiggles. Okay, so here what we're going to do is that we would add 21 over here, and then I'd basically just ask, hey, am I bigger? 21, or sorry, am I smaller? And the smaller item bubbles to the top, and swaps with its heavier parent. So there we go. We'd have 21, 23, and 29. And now 26 would be added over here because we have to maintain the property. 26 would swap with 63. And then 26 would swap with 48. And then we'd get 26 over here, and it'd bubble up until it hits 21. And then it can't swap any further. Right? Inserting is fairly easy. Okay? How do we remove from a heap? Right? We can remove from a heap in the following fashion. We can remove from the heap by basically saying, what do? We delete 21, we move 73 up here, and then we shuffle 73 down. How do we shuffle it down? Well, it's got to sync because it's heavier, and we swap it with its smaller neighbor. Well, sorry, with its smaller child. 73, 25, and then 73 swaps with the smaller child again. So 48. Sorry, so no. Yeah, 40. Yeah, what was it? 48, and then 73 now goes over here. Okay. So I'm going to go ahead and move on to the other theory question. Estimate the number of nodes visited to be visited when inserting a node into a binary heap with n nodes. Give a brief explanation. Okay, so the answer is log n. Now, why is this? Because a binary heap, if it's a binary heap, is a complete tree. Complete trees with n nodes have a maximum height of log n. So that means that we would visit so that means that basically the worst case scenario, where we're in a perfect tree situation, we would basically have to compare at maximum all the way to the root. So with a height of 3, so for inserting our 8th node, that would be 3 comparisons. Right? And now we can just simply generalize that and say if we're entering our nth node, it will be log n. Same thing, the same is with our delete operation. Estimate number of nodes to be visited while searching for the maximum element in a binary heap with n nodes. So finding the biggest thing in this heap. So notice that this heap and this heap are over here, giving us a bit of a hint, right? We have the, so right over here, so unlike a binary search tree, when we're looking for the biggest thing in the minimum heap, it's not really going to be helpful because we've got, hey, this guy over here, So we've got 63 over here, and then we've got 73 over here. We can't really tell by if we should go left or right to find the biggest node. The way we would have to do this, note that this 63 over here on the left could easily be swapped. Could easily be like over here on the right. Could swap there. Also, we could totally rearrange this tree. This 31 could be over here, and the 48 could be over here, and then we could swap the 63 with the 48, and 48 could be over here again. There's just tons of ways we can rearrange this. And look, the 73 is over here, right? We don't know whether it's going to be left or right. So the way we have to do this is that to find it recursively, we would say simply return the biggest thing, the biggest thing in my left subtree, return the biggest thing out of my compare the biggest thing out of my left subtree, compare the biggest thing out of my right subtree, and return the larger of those two. That means that we have to check every single node, so it takes O of n time. And for the record, I checked the specifications, and they say they want either C or Java. So nothing there for 2014. Let's check 2019. Cool. So they've got a sorting algorithm there instead but sorting is again something we've gone over. And if you take algorithms next semester, that'd be something that we'd want to go. I'm looking for more data structures. Find and merge. Looks like they moved away to doing more sorting elements. So that's interesting. Oh, but it talks about trees. So these kind of questions, if you want to go and look for stuff kind of by yourself, this is a fair way to do it. Now let's go ahead and take a look at my study guide again. Right? No, study guide again over here. And see what so that one just goes over to there now. Here we go. So the second link on this one. All right. So let's take a look at let's go over to question 2. Right? I'm just kind of hitting a lot of questions that I consider to be good questions over here. Consider insertion sort and merge sort. For each algorithm, what is the worst case scenario and what will be the asymptotic upper bound? What will be the worst asymptotic upper bound? In other words, what's the big O time on each running time if you know that the input is sorted, reverse sorted, and contains n copies of the same number. In other words, it's size n and contains n copies. So, for each case and sorting algorithm, state your answer and justify it in one sentence. So let's go over here. I'm going to do I for insertion, M for merge. The answer for merge is n log n in all cases. And the reason is because it doesn't matter what you do for merge sort. You're going to split it in half, and then you're going to split it in half again. You're not going to check anything when you're splitting it in half, but basically you keep splitting it in half, and then you merge those halves together, right? It does not matter what the contents are. Merge sort is just going to simply merge them together. Does not care. Make sense? It's going to just run. It's going to run the same way regardless of the contents of the actual contents of your array, okay, or your list. It doesn't really matter. Okay. Now it might run differently whether you give it a linked list or an array list, but hey, that's fine. Now insertion sort. Although I think internally it probably handles those. Insertion sort does actually matter. Like, so over here for insertion sort, if things are in order, right? We'll go to 1, we'll try to push it down. We can't. Go to 3, try to push it down. It's already in place. Go to 4, compare it to 3. Can I push 4 down further? No. Go to 5, can I push it down further? No. 6, no. 100, no. We're done. Basically, we check each item see that we can't move it. So the way insertion sort works when everything's already sorted is that we go through each item, see that we can't check it against the one before it to see if we can move it down further, see that we can't, and go on to the next item. We do that for n items, so we know that when it's sorted, that insertion sort takes O of n time when it's sorted. Now, when it's reverse sorted, it's a different story. That's actually like our worst case scenario, right? Let's take a look at like 7, 6, 5, 4, 3, 2, 1. What we would have to do over here is that we would have to take the 6, put it before the 7, then we would have to take the 5, compare it to the 7, then compare and say, okay, swap there. Then compare it to the 6 and say, okay, we got to swap down and push it down here. 4 the same way, we'd compare 4 against 7, 6, 5, then 3 would be against 7, 6, 5, 4, and then 2 against 7, 6, 5, 4, 2, 7, 6, 5, 4, 3, and so on and so forth. Basically, we'd have to sort every single item a maximum amount of times, which is the whole, it would be the 1 plus 2 squared, be the 1 plus 1 plus 2 plus 3 plus 4 plus 5 that we've seen since the beginning of the semester, which means this takes O of n time. If the list contains n copies, and I'm assuming that by this that the author means that we have n, that basically the array is size n and there's identical n elements. Well, here's a list with a bunch of 5s in it. Can't push 5 down, can't push 5 down, can't push 5 down, can't push 5. It's the same as our sorted case. Make sense to everybody? Okay, cool. Suppose we have a number of sets, constant time, right? Number of lookups. I'm just skipping because I'm looking for a good one over here. Aha! Suppose you have a hash table and inserted some elements into our hash table, right? So when you inspect your hash table, you see that the result that looks as the picture below. Being a good student, you realize this is a problem. So, what is the problem? Give an example of a hash function that will give rise to this behavior. What would be a better hash function? I'm going to do an a minus a over here. What is the collision strategy that is being used over here? What is the collision strategy that is being used to resolve our collisions over here? Chaining, exactly, right? Each of these entries is a linked list. Right? Each of these indexes gives us a linked list.
What's that?
So, what is the problem with what we have here? What's gone wrong? And you can unmute yourself if you want to give me an answer, or you can type it.
That's a bird.
Lots of collisions. That's right. We've got tons of collisions. Right? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 items. Yep. We've got 13 items and we've got a super amount of collisions. Actually, which indice is there any pattern with the indices that have or don't have any items in them? Which indices even items. So right, even items have stuff in them. So index 0, index 2, index 4, 6, 10, 12, 16 all have things in them. Right? Whereas all these odd indices are pretty much guaranteed to not have anything in this. I mean, could be. You'll see yourself out. All right. So, now, what is an example of the hash function that could result in this? So, given a key x, what could have happened? How could we have gotten this? Right. Well, let's look at these. The 0 and 30 went to 0. 21, 31, and 1 went to 2. 2 went to 4, 33 and 63 went to 6. It's easier to see this when we say it out loud, but like all the things that end with 0 are together.
all the things that end with 1 are together, and all the things that end with 3 and 6 and 8 are all together. So the 0s went to 0, the 1s went to 2, the 2s went to 4, the 3s went to 6, the 5s went to 10. Yep. We can double the... Yeah, we can essentially say double that number, right? And then we can mod by 20, right? So we can say x times 2 mod 20 gives us this issue, right? So that goes for this. 21 is 42, 31 is 62, 1 is 2 if we double them, and then mod 20, it will end up in here. Actually, hold on. Mod 20. So 31 would give us 61. 31 would give us 61. Sorry, 62. Yeah. And then that would give us index 2. What about doubling this? 63, 23. So doubling in this case, we end up with 30. Yeah. So doubling and modding by 20 seems to work just fine. Just double checking. What is a better hash function? What would be a better hash function? Using a prime number. Okay. So h of x, x what? What can we do? We could mod... Yeah, modding by 19 doesn't seem like too bad. Yeah, we'll waste the 19 slot, but whatever. And then we would end up with things going that 17 times int mod size. So multiplying by 17. Another one is that's suggested is multiply by a prime number. And then we would get, and then multiply x. 17 times x. Mod. Mod 19. Important if you're, mod by the size of this, which is 20. So important thing to remember is whenever you do modular arithmetic, is that the computer is interpreted as the same level as multiplication, so you want to put it in parentheses. Yeah. The answer is pretty much anything will be better. Okay. So that's one. Let's see. So those are the good ones. I'll come back here to this one if I want. Oh, here. So suppose we insert an element x into a binary search tree that does not already have it. Suppose we then immediately delete x from the tree. Will the new tree be identical to the original one? If yes, give the reason in no more than 3 sentences. If no, give a counterexample. Draw pictures if you necessary. So, let's go ahead and... So, I would say that basically that... First off, let's leave aside the whole ship of Theseus debate, whether or not is it essentially the same if we insert and delete it, and that makes no changes to the structure of the tree. We'll leave that aside for the philosophy majors. Okay. Have the atoms in my computer been permanently altered in some way by adding and then removing the tree? Not gonna do that. Not gonna go there. But the abstract mathematical structures are the same. I would say yes if we insert an item. Let's go ahead and create a abstract tree, right? And now let's go ahead and say if we add any node to any position in this tree, it doesn't matter what the value is, it's going to be a leaf, right? Or it could just like come out over here. It doesn't matter. Okay? So now if we go down through and delete it, we'd be deleting a leaf which does not change the structure of a tree. It just removes it, doesn't pass any information other than to... It would return a null, which it would tell its parent to replace it with a null, which is the exact same state it was in before. So that is the answer for yes. I think actually this is a open-ended question. The answer for no would be if the tree is self-balancing. That would be the counterexample for no, I think. If you considered self-balancing trees, which we did not discuss, but if, I think this is one of those where basically you can say, because they don't specify whether it's self-balancing or not. So I think this is one of those questions that depend on your professor. But if I were giving this question, I'd accept yes or no and I'd accept no if you'd said it was self-balancing or something like that. We didn't go over self-balancing, but I never penalize a person for knowing more than they should. Okay, so let's have a heap with two values, v1 and v2, distinct. Let 1, 2 be the heap. It'd be the heap you get if you insert v1 into... Okay, so we've got a heap. Let the heap be 1, 2 if you put in the first element then the second element. And then 2, 1 be the heap if you insert 2, 1. Be the heap if you insert 2, then 1 into the heap. Give an example of such that where you insert these two items in different order, and so the heaps don't, and so the heaps are different. No justification. Just draw the heaps. H, 1, 2, and 2, 1. Okay, this is super easy because this professor did not specify that I cannot use the empty heap. There we go. And now V1 is going to be 1, and V2 is going to be 2. Let's see, actually. No, that won't work. That won't work. Because, I wish that would work. But you put in V1, it will swap. It's going to swap no matter what. Okay. What we need is then something that's going to... Let's see. What we need is a structure that's currently looking like this. So... Because the second node... So we need something that will look like this. So let's say 1... Let's say with... let's go with 10, 20... If we do 30, 40, let's see. 30, 40 would... Yep, that will do it, I think. So let's try 30, 40. So 10, 20. If we do 30, that's fine. And now if we do 40, it's fine. And then if we do 10, 20, 40, 30... Hey, look, they're not the same. Right? So, heaps unlike heaps like trees, it really depends on the order in which you add stuff. All right. All right. So, suppose you have a graph like this one below. The graphs, the dots signify some part of the graph you don't know exactly, but it's not a straight link. Right? You know, however, there are many paths from the start to the goal. You also know they tend to be rather long. Suppose you want to implement a program that searches for a path and returns the first one it can find. You have no need for finding the optimal path in any sense, just any path will do. Would you want to use breadth first search or depth first search as the basis for your program? Justify your answer in at most 2 sentences. Well, they say it doesn't matter if it's the optimal one. So it searches for the path and the first one it will find. So let's see. So let's talk about breadth first search and depth first search. Which one would be better for this case? DFS. All right, what are the pros of DFS and using the cons of DFS over here? Why would we want to do depth first search here? Because I think... Yep. Somebody gonna speak?
I was just gonna say depth first search will go from the start to the goal until it can't anymore, and then won't waste any time like essentially it'll only explore up to where it needs to, and then it won't. Like if it reaches a dead end, we won't have to wait for, if it was breadth first search, then we'd have to wait for everything else to catch up as well.
Right. So for depth first search, what we're looking at is that if we look at the structure of this graph, this is making an assumption here, okay? The assumption is that so first off, we're going to assume that there's not many paths. Sorry, everything starts at start, and then we've got this middle section, and what we're assuming is that this middle section doesn't have any dead ends, is kind of here. But even if it did, that still makes the case that basically everything is single links to this, right? To basically get to the goal, if we look at this kind of like a tree, a weird tree, then we'd basically have to go down to the height of the goal. And we'd have to basically go through each level of the tree if we were using breadth first search. Or each level of the graph, so to speak, if we're using breadth first search. Yep, we're looking, essentially, once we hit this endpoint, this goal, once we find it, we'll be able to stop. With breadth first search, we'd have to check all the ones that are 1 away, then all the ones that are 2, then all the ones that are 3, then all the ones that are 4, and so on and so forth until we got to the end. And it really depends on the structure of the graph, but in this case, I would lean towards using depth first search, just simply because of the shape, and the fact that it's directed. Now, here's a question I would do. What if all the edges were undirected? Or bidirectional? What if every single edge goes like this? Does that change anybody's answer as to their strategy? Because it changes mine. But that's also because I am a trickster. And I like thinking outside the box and doing things that I'm told I can do, not explicitly told I can't do. In this case, I would use BFS simultaneously from the beginning to the end, which is useful when you're trying to find a connection between two points. Which is a pretty cool thing I could do. And again, it depends on the surface of the graph. Again, we're not trying to find the optimal thing, but a breadth first search and a depth first search would find what we're looking for. But the question is, does breadth first search or depth first search find the shortest path first? And so that's a question that basically you should probably check. I mean, we're not specifying whether we're not looking for the optimal path, just any path. If we're looking for the optimal path, which one would we use?
We'd have to use breadth first search.
Yes, in that case we would use breadth first search because we'd hit it on whatever level we matched it at that point. So there's whole lots of kind of situations where that would apply. Okay. So let's go ahead and I want to check. That final isn't for that class anyway, so for this class anyway, so not that you would get much out of it. So let's go ahead and check this one. All right. So we'll skip down here. In this course, I like this question. It's a lot like some of the questions I'll be having on the exam, and a lot like the questions you got on question 2. In this course, we've seen many different data structures. We've got lists, linked lists or array lists. We've got 2D arrays, which are technically a data structure. We've got our stacks, queues, and hash tables. We've got our trees, our binary search trees, our undirected graphs, our directed graphs, and our directed acyclic graphs, or DAGs, right? Those are the kind of graphs that we have in the last problem, right? Directed acyclic graphs are the ones that basically look like this, where everything basically you cannot backtrack anywhere. There are no cycles. So there is a directed acyclic graph. Everything's going from the start to the finish. There's many ways to get there. Many, many, many ways to get there. Some are shorter, some are longer. Right? But they all end in the same place. Okay. So let's go ahead and go through this. We want to, so for each of the following applications, indicate which of these data structures would be the most suitable and give a brief justification for your choice. For data structures like trees and graphs, describe what information is stored in the vertices and edges. And if the edges are weighted, describe what information is stored in the weights. All right, and this is from something in Washington, hence the Puget Sound highway system. Map of the Puget Sound highway system is used to display traffic travel times on a web page. The map displays the principal cities, the intersections, the major landmarks, the roads that connect them, and the travel times along those roads. Travel times along the same road may be different in different directions. What data structure is best for modeling this? A directed graph. That's right, because we're looking for relationships. Right, and specifically over here, we're looking at a directed graph as opposed to undirected graph. So, but that's fine. Now, here's the question. What are the nodes, what are the edges, and what are the weights? So, the nodes are all the destinations, right? These principal cities. Yep. Nodes, intersections, cities, and landmarks. Roads are, I think... Yeah, roads are edges. There you go. So the roads are our edges, right? Right? It's our remember, graphs are all about relationships. Which is that, so our nodes are a location, and the relationships is how are they related? How do we get between them? And that's right. The weights, in this case, are equal to the time, right? And because it's a directed graph, and this last clause is satisfied by having it be a directed graph, right? Right. Going into a city during rush hour, during morning rush hour takes longer than getting out of the city. All right, chessboard, an 8x8 board used for a game of chess. Each square is either empty or contains a chess piece. We may have done this. What is 2D array, totally. Totally a 2D array. All right. So, question C. A computer model showing the dependencies between the steps needed to assemble a B787 at Boeing's Everett plant. Yeah, 2D array was an option. Right? 2D array over here. Second option. Computer model showing the dependencies between steps needed to assemble a plane at Boeing. Not a Q. All those are kind of in the right direction. What does it mean by dependencies? Now we're talking. What steps need to be done first? Not a heap. So it's a special type of directed graph. Yeah, it's a directed acyclic graph. Directed acyclic graphs are what they're used for if we're going to model if we're going to use it as a data structure to model something, is basically, let's say we need to do step A before we can do step B and C. B has to be done before D, and both of those have to be done before E can be done. Yeah, acyclic, then do Kahn's algorithm is one way to do it. Kahn's is one way. Yeah, Kahn. Okay. Okay. A list of the legal words in a Scrabble game. We want to quickly be able to check whether the words used by a player do in fact exist in the list. And so, say the user says kerfluffle. A hash map, kinda. I'd give half for a hash map because a hash map is used for counting. What are we doing with that
what are we doing with but we want to just simply check if it exists or not. Actually, do we have that as an option? Hash table. So yeah, I'd give it. Yeah. Hash set is the one I'd be looking for if I gave you an option, but set, it didn't distinguish between set or mat. So my bad. So yeah, hash table is what the answer would be for this exam, but a set is what we want to use, a hash set specifically. Because set hash map and hash set, honestly, they're the same. And just a hash set is just a hash map where we don't care about what the value is. We only care about the key. Description of inheritance relations between classes and interfaces in a Java program. A tree. Yep, it is literally a tree because of the way these relationships work. You can only extend you can extend multiple interfaces, but you can't extend classes. So maybe a DAG. I would also accept a DAG, but a tree. A history list recording sites visited by the user of a web browser. As new sites are visited, they are added to the list. This list also supports the operation of going back to a web page that was previously visited before the current page and going forward to the next page. A single stack won't do it for going... So stack, if you use two of them, will work here. It would be a very boring graph, but a graph would work. A linked list would definitely work here. There's a lot of good answers for this one. But using a pair of stacks would work. Using a linked list would work. Using a array list would be less effective here. A graph, in this case, again, would be rather boring, although it would be interesting to see a list with a history function that uses a graph to tell you what you opened, when you decided to open what tab. A link, you're not going to get a cycle in a linked list using this. You just simply think about the way that the forward and back functionality work here. You can only go back and you can only go forward, right, to a single page in that same tab.
Yeah, but my thing was more let's say I go to a web page, I go to another web page, I go to another web page, and then I go back to the first web page without using the back functionality. I just type in that new web page.
Oh yeah.
If I use a linked list, that would make this so good.
Well, what it does is that it stores that web. If you do that, it just stores that web page as an additional instance.
Okay.
That's what happens, I think. All right. Let's see. So nodes in a integer binary tree can be represented by the following data structure. We've got our binary search tree. Honestly, it doesn't matter if it's a binary tree or binary search tree here. Got our binary tree, an item, and a left and a right. We can complete this method, breadth first search, to perform a breadth first traversal of a binary tree, also known as level order traversal, right? And print the node data values in the order they're reached during the search. In your solution, you may create and use instances of other data structures and their operations if they are useful without having to give the details of their implementation. Right? That's just saying that basically go use everything you know how to use. This is breadth first search. And the kicker here is that it's tree, so you instinctively want to be recursive, but that's the wrong decision here. Instead, we just simply want to use a queue. Actually, why am I writing it on the screen over here? Because my handwriting is terrible. So let's go ahead and just simply write public void BFS node E node. Here, we're just going to want to write breadth first search like we did for our graphs. So, okay, prints out the node or the nodes in the order they are received. So Q, and we don't even have, and because it's a tree, we don't even have to keep track of what's been visited or not. It's because there's going to be no risk of edges that lead backwards. Q is equal to Q of nodes over here.
Blazer, you sound so distressed.
I think he accidentally knocked down the key selector. Are you sad?
Q dot.
Knocked it down?
And they use
You want a different game?
what they. It's a linked list. So, but what are the Q operations? It's not NQ and DQ. It's pull to get out. Is it add? Probably. Q dot add node. So let's go ahead. While Q dot is empty is not true. What are we going to do? We are going to node e q current is equal to q dot poll. I mean, if you use NQ and DQ on the exam, I'm not going to really care. I'll know what you mean. So node current is equal to q dot poll. We get current out. And then simply we say, hey, system.out.println current.data to get out its data, and now we got to add its children to that, which is just done by saying, hey, q dot if current, and here we actually have to check our children because otherwise we're going to add null. Or we can just be lazy and say, hey, if, yeah, I'm going to be lazy. If current is not equal to null, I'm going to allow nulls in my queue. If current is not equal to null, print it out, and then q dot add current dot left, q dot add current dot right. Make sense? Why I have that if current not equals to null there? Because what I'm going to do is I'm going to add left and right regardless of whether or not they're null, which is perfectly fine. If they're null, I'm just adding null to the queue, and when I get to them, it's going to be a null entry. And I'm just saying, hey, if it's not null, do something. But if it is null, I'm just not going to do anything because I'm lazy. Is this safe programming practice? Probably not, but honestly, it was the quickest thing to write, and it works. Okay. If it was on paper, we'd be doing something like this, which is, here is a graph, please draw the picture of it. Right? And I'll go ahead and do that just simply so that you understand that you do this, because what I might do, yeah, that's a good one. So what I'm going to do is, there's no reason why I can't make you do that and then do an operation on it. So let's go ahead and draw this. Right? So here we have an adjacency list, right? So we have so now draw the picture of the direct graph. So we have 4 nodes, A, B, C, and D. You thought I was going to put D there, but no, I'm going to change things up. So whatever. So A connects to B, C, and D. B connects to A. Let's go ahead and draw little circles around these guys to make them, feel nice and safe. Right? C goes to B and D goes to nobody. Right? Is this a directed acyclic graph? So I've got some opinions here. No and yes. So the question you have to ask yourself is there a cycle? Yep. A, B, A, or A, C, B, or A, B, C, B, right? We can go around and around on between A, C, and B. So that means that we've got a cycle, right? So let's see. Can I remove things? What would have to be removed for make this an acyclic graph, I wonder? What I would have to remove, let's see. First off, we'd have to remove, let's see. I'd have to remove this and this. And that would make it a directed acyclic graph. If I just removed A, yeah, this would be a directed acyclic graph, but I feel uncomfortable with it not all going to the same location. What are you watching? Aha. All right. So, I think this is a good place to stop for here. I'm going to upload these videos. I'm also going to share them with all your other classmates who are in different sections so that they can have access to this. All right. I think Monday I might reserve for questions about the specific questions about that you might have about the final exam. So, as opposed to doing any kind of specific thing. So, if you look up exams or if you go over the pages in the study guides and you want me to hit any specific questions, please tell me. Okay, does that make sense? Right? So, Monday's going to be reserved for student questions. Sound great? All right, I'm going to go and immediately upload this so I can share this with everybody.